So here I have problem number 12, and this is dealing more with piecewise functions, and piecewise functions are an important concept in Algebra 2 as well as pre-calc. So here I have a function, right, that's given. It's more like a piecewise function. I guess it could be a piecewise function if it's split, but you will see if it's continuous or not, right? So we have -1, comma, or we can say if it's less than or equal to -1, and then we have 3x plus 2, comma, if absolute value of x is less than 1, and then we have 7 minus 2x if x is greater than or equal to 1. So we have this over here, and now we want to graph this, right? We want to graph this function over here. So we have these different restrictions given to us. So the first one, if we look at this, it states that y is equal to -1 again, which is really just a horizontal line, right? Whenever y is equal to a constant, that's just a horizontal line. If x is less than if x is, I think I missed an x here. Yeah, if x is less than or equal to -1. So at -1, right? We know that it's gonna be, so this point over here is gonna be -1, comma -1, right? And really anything before that is also gonna be part of this restriction here. And looking at the second one, we know that if x is, if the absolute value of x, so that we're looking at the absolute value of x. And so primarily, if we look at 0, absolute value of 0, right, is just 0, so that doesn't meet the criteria. So then we can plug 0 here, and we see that 0, 2 is a point, right? 0, 2 is a point, and really, obviously -1. If you do put -1 here, you see that 1, unless you had this sign, which you do not. So if you do put -1 here, it does not meet the criteria. However, if you do put -0.99 or anything like that, that does meet this criteria. So we still say that -1, -1 is a point, and then really we just connect. In this case, we will just be connecting these two points here, right? So we have that. Now we're looking at, so let's just look at x is greater than or equal to 1. So if we do put this, when we're looking at 1, we see that 7 minus 2 is 5. So we know that 1, 5 is also a point somewhere here. So this is 0, 2. This point over here is 1, 5. And so we graph this here as well, right? This would just continue as well. At times what happens is when you're not sure, there may possibly be a hole, right? So therefore you may want to check, for instance, even though I know that we're really talking about this restriction when I substitute 1 in, however, it's always good to substitute 1 into this as well, although obviously it doesn't say that it's equal to 1. You still want to substitute 1 in, and you see that it's 5. So it still satisfies it. Now, for instance, if you had put 1 here and you got something like, I don't know, 4, right? Then you would put that whole symbol of the whole, because you're saying that it's approaching that. But the fact that you're plugging 1 in and you're still getting 5, and you plug 1 in here and you still get 5, indicates that really this one is continuous. There's no discontinuities in this piecewise function, right? So you have everything being connected so far. And then we can plug in anything else. For instance, let's plug in 2. Well, we see that it's 2, 3, right? So that's going to be somewhere here. Obviously 2 is greater than 1. And then we can plug in 3 as well, and we see that 3, 1. So our function is looking something like that, and obviously this one's will just continue here. So that's how it looks like. Now our x-intercept here, right, is the value of x when y is set to 0, right? So it's a value of x when y is set to 0. So really, when we're talking about our x-intercepts here, we're seeing at which points does the graph cross the x-axis. So there's one point here that we can visually see, and then we know that there's another point that it will sometime cross this x-axis, right? Because it's infinitely going here. So we're really saying that 7 minus 2x it should equal 0, and we're solving because again x-intercept is the value of x when y is set to 0, right? When y is set to 0. Similarly here, we are looking at for this one, because it's between 0 comma 2 and -1 comma -1, we are looking at so we were looking at this one, 3x plus 2, right? Because that makes sense. If it was anything before -1, then we would be looking at somewhere here. But we don't really care about the first one. We're looking at the second restriction to find the second x-intercept. So our second equation is 3x plus 2 is equal to 0. And so let's just solve that. So we see that 2x goes there. So we have 7 is equal to 2x. Therefore 7 over 2 is equal to x. And then we have x is equal to -2/3. So we have these 2 points here, and so really our x-intercepts are 7 over 2 comma 0, and then we have -2/3 comma 0. So those are our 2 x-intercepts, right? And that's an important concept because you understand that your graph, when because it's going to be continuing here, it's going to cross somewhere here. So this point over here is going to be 7 over 2 or 3.5 comma 0, and this point over here is -2/3 comma 0. So those are your 2 x-intercepts. Your y-intercept we already know is 0 comma 2. Your domain here is a set of all real numbers. Again, we were lucky that there weren't any holes. It's always good to check by plugging the 1 here, although it's not included, but we saw that it was 5. So there are no discontinuities. Domain is a set of all real numbers, and a range is a set of all real numbers such that y is less than or equal to 5, right? Because 1 comma 5 is really going to be your greatest point here, right? You see that this point over here is the greatest possible value. So your range is y is less than or equal to 5. So that's the first example of a piecewise function, right? I could go over another one. So let's look at number 13 here, right? So number 13. Well, number 13 here states that y is equal to, we have x squared plus 1, and then we have if x is greater than 0, and then we have -2x plus 2 if x is less than or equal to 0. So we have those 2 points here, and looking at these 2 different restrictions, right? So we have these 2 different restrictions, and as I said before, it's always good to plug in 0, right, in both equations, right, to see if we have any discontinuities as we move from one restriction to another. So let's just make a sketch here. So we should look at 0. So when we plug 0 here, we see that it's 0 comma 1. When we plug 0 here, we see it's 0 comma 2. So there is disparity for sure. Obviously this point over here is the one that's not going to be the hole, right? It's going to be the filled circle, because here x does equal 0. So we have 0 comma 2 as a filled circle here. However, when we plug 0 here, we have 0 comma 1. There's going to be this open circle here, right? The hole. And then for the other values, x is equal to 1, 2, you just plug them in. So you plug x is equal to 3, right? And you see that overall, because this is more like a quadratic function, it's going to be increasing at a much larger rate as the value of x increases. So really, when we're talking about this, we will be saying that it's going to be something like that. It's going to be increasing much faster as x increases. And then your other restriction here states that x could be less than or equal to 0. So we can take any value here, but this is really just a linear relationship here. So we can plug in any values, and we'll see that we have a line that extends this way here. So obviously this point is actually a point here. This one, if you don't see it, I can make it better. We have, it's more like a circle here, right? The whole concept of a whole concept of a discontinuity here, right? Again, because at we want to see what happens as it approaches that value. So even for this function, if we, for instance, if we say that limit as x approaches 0, it does not exist, because as you're approaching from the right, it's approaching this value over here, right, which is 1, and as you approach from the left, right, you're as you approach from the left, you're approaching the value 2, and those one-sided limits are not equal. Therefore the limit of f of x as x approaches 0 does not exist. That's just there, I wanted to point out. So but we have our graph here. That's how it looks like. So our x-intercept we don't have any. Y-intercept, we do have one, that's 0, 2. Domain is a set of all real numbers. As you can see, even at 0, that is included, right, because x does equal 0 at this restriction. And then a range is a set of all real numbers such that y is greater than 1. So it's really all real numbers. Y has to be greater than 1. Obviously y is not, it's close to 1, right, but it's not actually 1 because there's a hole here. So those are good examples of piecewise functions. Again, their characteristics, and also the concept of a limit to see where the discontinuity is, where the function actually breaks. So thanks for watching.